Episode 2, Downstream Petrochemical. In the last episode, I discussed the upstream petrochemical industry. This episode is about the downstream petrochemical industry, which takes crude oil and transforms it into usable products. The setting of many downstream petrochemical careers is the refinery, which are massive chemical plants. Some of them are large enough to have their own zip code and contain enough pipe to stretch back and forth across the continental United States. Shown on the slide is the Chevron facility in Baytown, Texas, and the ExxonMobil facility in Baton Rouge, Louisiana. Also shown is a map of the refineries in the U.S. As you can see, there are plenty in the southeast, but again, Florida conspicuously comes in at 0 refineries, and my suspicion is that the reason is tied to state-level politics. Before we dive into specifics, let's first talk about a critical step that links upstream and downstream. Some call this midstream, and it involves transport of crude oil from the drill site to the refinery. This map shows some of the miles and miles of pipeline to refineries in the Gulf of Mexico. Looking at this map, can you think of any problems or challenges for the chemical engineer? Pipe is made out of metal, and it is lying in salt water, which is a corrosive environment. If the pipe rusts and develops a hole, you could have an oil spill. How do you think engineers maintain and monitor this pipe? How often do you think it has to be checked? Another issue deals with the physical properties of crude, which is very viscous and sludgy. Therefore, an engineer has to calculate how much pumping power is required to propel this crude through the pipe. The engineer also has to devise a strategy for detecting the presence of blockages in the pipe without seeing them, and brainstorm ways to clear them. Remember, the pipe is solid and opaque. You can't see through it. Fouling is a word for buildup on the surface. In this case, fouling decreases the effective pipe diameter, which causes more friction and therefore increases the energy required to pump the fluid. Once you finally have the crude oil to the refinery, you have to figure out what is actually in it. The different colors of the samples of crude are an indication that the composition is different. There are more molecules in crude oil than anyone cares to count. Engineers give up on trying to identify them all and instead classify them by type, including paraffins, aromatics, naphthalene, resin, and asphaltenes. Gasoline is made up primarily of paraffins and aromatics, but asphaltenes can be disastrous for your engine if they make it to the final gasoline product. In the last video, I warned you about some of the jargon in the petrochemical industry, and here is a fun example. Crude oil with less than 0.5% sulfur is called sweet and ready for refining, while crude with more than 0.5% of sulfur is sour and requires pre-processing. One of the most important process units in the refinery is the FCC, or fluidized catalytic cracker. This is a huge reactor that cracks the crude. In other words, chops large and bulky molecules into smaller ones. In general, the smaller molecules are more useful. After cracking, there's a mixture of many different molecules which need to be separated. This occurs in another key process unit, the distillation column. Distillation columns use heat to vaporize a portion of the liquid mixture for purposes of separation. As you can see on the simplified process flow diagram, the components with the lowest volatility, that is, tendency to vaporize, remain at the bottom of the column, while volatile components work their way to the top of the column. Automobile gasoline is the most well-known product, but this process produces many other useful products as well, including jet fuel and diesel fuel. Also produced are propylene and styrene, which can be polymerized into plastic and styrofoam respectively. Also, cyclohexane, vinyl acetate, phenol, ammonia, benzene, toluene, and xylene. Many of these molecules are great solvents. For example, toluene and xylene are main ingredients in paint thinner. These molecules are also used to make rubber and ink. To conclude this episode, I'd like to show a video from YouTube titled An Overview of the Refining Process.
From the outside, an oil refinery looks like a small city. A city composed of pipes, tanks, and towers. But if you went inside, you might be surprised to find one of the most technologically advanced industries in the United States. Here, engineers and scientists have figured out how to turn raw crude oil into the valuable fuels, lubricants, and components we need to make millions of products. Refining begins with a process called distilling. After oil is superheated, it becomes vapor. The vapor is fed into the distillation unit. As it rises and cools, the vapor turns back into a liquid. Using stacks of trays, the liquid is easily collected and separated by weight. The lighter and medium weight liquids require less processing before they're ready to be used in cars and trucks. The heavier liquids need more processing to become useful. A process called cracking is used to maximize the usefulness of heavy oil. Heavy oil has long strings of carbon and hydrogen molecules. Using a catalyst, these molecules can be broken into smaller chains, transforming the heavy oil into lighter, more valuable fluids. Reforming is a process that increases the amount of gasoline produced from crude oil. One of the products separated in the distilling process is a liquid called naphtha. The number of carbon atoms in naphtha is about the same as the number found in gasoline, but their structure is more complex. Reforming rearranges the naphtha molecule, turning it into a usable, gasoline-like molecule. Blending is a process of mixing different refinery products to make finished petroleum fuels. Gasoline, for example, is blended to achieve octane standards, creating the grades of gasoline you see at the pump: regular, mid-grade, and premium, that are necessary to meet the needs of specific engine types. Treating is a process used to produce cleaner gasoline, which helps protect both the environment and our health. Gasoline molecules contain impurities like sulfur that can be removed. When the molecules are heated and come in contact with a special catalyst, a chemical reaction occurs that strips the sulfur away. These sulfur compounds are used as fertilizers and in pharmaceuticals. Nothing goes to waste in a refinery. In fact, by expanding existing refineries and improving their efficiency, we've increased production of refined products by more than 40% since the 1970s. So the next time you drive by a refinery, think about the scientists and engineers who are helping to efficiently transform raw crude oil into the fuels and products we use every day. Their innovative work helps keep prices low for the many things we use in our daily lives. And think about how refining, like other types of manufacturing, supports entire communities. Put it all together, and you'll see how refineries keep America moving.